Hello, everyone. So my name is Aaron Wetherold. I'm an Azure HPC specialist working with customers in the energy sector. So I'm a teammate of Manish's. Today, what I'd like to cover is essentially what we spend most of our time working with customers on, which is really how to migrate and optimize the current HPC workloads that they have into the Azure cloud, and really how to best take advantage of the benefits of running those workloads in Azure. Let me know if you're not seeing the slides transition. So I'll cover some of the most common HPC scenarios that we encountered today. So Manish covered some of those, but I'll touch on a few of those that I think that are important to re-highlight. And then some background in the current infrastructure. I'm going to cut that part a little bit short so we can focus on really the meat of the presentation, which is the main topic, which is that phased approach that we take when moving workloads into Azure. So this slide will look familiar after we went through Manish's presentation, but again, I'd like to cover some of the four main scenarios that we're typically looking at or encountering in the energy sector. So as Manish mentioned, a very common and predominant workflow is going to be the oil and gas upstream workflows with seismic processing, imaging, reservoir simulation, and things like computational chemistry as well. And then we see in the energy field and development, there's a variety of CAE type of workflows with CFD and FEA solvers, and also thermal analysis dominating that mix. But then as we see more investment in renewables, we also see like an uptick in workloads that include things like weather modeling, simulations, and forecasting. So they're using that to basically not only deliver better wind turbine designs, but also figure out where to place those wind turbines to maximize the power production. Looking at things like upstream digitalization, so that's where we're looking at analytics, resource and production optimization, as well as asset performance to maximize the efficiency that we see in production, things like generation and distribution of energy. So here we'll see workloads where customers are looking at their input crude products, looking at what the refined products would look at on the outbound side, and then determining what's going to meet from a profit standpoint and maximize not only the efficiency, but the output of that production. And then finally, mining as several areas for HPC-like workloads, including things like exploration, development, extraction, as well as the standard production. So let's take a look at some of the Azure infrastructure we use to architect the HPC workloads. And again, I'm not going to go into a ton of detail here in the interest of time, but when we look at that HPC resource stack that Manish mentioned, and those are going to be very typical components that we see in any type of HPC workload. Sort of the heart of that is going to be the optimized compute. We have one of the things that we're very proud of within Microsoft Azure and the HPC arena itself is that we tailor make and configure these specific SKUs for HPC type of workloads. So these are not SKUs or VM sizes that we adapt for HPC, but they're actually designed that way when we're looking at what type of computational do we need. Is it CPU based, GPU based? Is it memory bandwidth or computationally intensive? With that, obviously we need high performance storage to not only read the input data out of, but store the output results. So that is going to form a big portion of what we're using within the HPC arena. Workload orchestration, we'll talk about this as we look at the movement of workloads into Azure and into the cloud. And then fast secure networking to really tie everything together. So Manish mentioned InfiniBand networking. So that's a key component when we're looking at the tightly coupled types of MPI jobs. but also we're leveraging ExpressRoute to actually get the on-premise connectivity into the Azure cloud. And then one of the examples that we'll look at is really using transformative services like Azure Machine Learning and Machine Learning Compute itself to actually enhance the capabilities of the HPC stack. So with the background info in place, we can really move on to the core part of the talk, which is really how we migrate and move working with our customers to successfully and really efficiently migrate and optimize the HPC workloads into Azure, and then be able to leverage all of the advantages that we outlined. And we'll take a look at some of those examples as well. So, this is the part, like I said, that we spend a lot of time with customers, not only talking about it, but architecting and actually performing the move itself. So as we look at that process of moving these HPC workloads into the cloud, one of the things that we have to recognize is that there's very few applications that just jump directly to cloud native status unless you develop those that way. So for the majority of the HPC cloud, HPC workloads that we're looking at, we really transition through, I would say, at least a couple, if not more, of these stages that were outlined as we move those into the cloud. And the other thing that I should mention is that for many of the applications, the final goal may not be to reach the fully cloud native status or model, because they may operate quite well and efficiently in either the hybrid workflow or sort of a cloud hosted mode. So as we move sort of from left to right, you have your existing apps, and then in working with customers, that really the first step and quickest way into Azure is to replicate the existing setup that they have on premise with the closest components in Azure, as quickly as possible, which reduces not only the time to test production, but also doesn't require any significant changes to the application or workflow. That's really what we're talking about when we say clone to the cloud. The next real step is going to be what we call the hybrid workflow. And it's really about optimizing where possible in terms of things like connectivity, VM sizes, storage configurations, et cetera, while maintaining the on-premise functionality and really bridging the two environments via that workflow. As you move further to the right, then you sort of transition into a sort of cloud workflow where that optimization or the further optimization really is going to lead to really fully leveraging the benefits of running in Azure, including things like job and workflow VM types, full elasticity, and then per job orchestration models for both the compute and the storage. And then that last state where we're terming cloud native apps is really what I would say a fully optimized state where the application would either be refactored and modernized to fit into those sort of native cloud constructs. All right, so what I'm gonna do here is really walk through a sample application from a customer workload. This is a sort of genericized version of a typical workflow that we'll see using existing seismic processing or imaging architecture. So the goal really for the customer here was to take what they consider higher value seismic workloads and then rapidly move those into the cloud. So at the bottom here, we have what you would consider your typical on-premises compute cluster setup. It's got an existing scheduler, a head node that's mated to Lustre parallel file system, and then a number of smaller, lower latency NAS storage volumes. In the way that the job submission flows is the user will submit jobs from their user workstation into the scheduler. The scheduler distributes that workload across the compute cluster resources. So fairly typical setup in terms of on-premise HPC. So as we start sort of the movement into Azure, the first phase of that application migration really involves replicating the functionality of the on-premise setup into the cloud. And while I say that we don't do a ton of optimization here, a lot of times there are pretty easy windows where you can optimize as you're building the new architecture up, while you're still maintaining a very similar strategy to the workflow that's on premise. So here we're really aided by the express route connectivity into Azure, deploying our Cycle Cloud server and scheduler template that automatically spins up and configures things like HPV3 or HPV2 Azure sized nodes in response to job submissions from that head node. It's going to monitor that workload, and then it can scale down the compute cluster once the job is complete and that the compute is actually idle. So once that job is finished up, the system knows there's no more workload to be done and can effectively spin all those compute resources back down. We're also leveraging here Cycle Cloud to spin up a durable Lustre IaaS cluster for parallel file system storage, so that mirrors what they have on premise. And then we can also back that data up with Azure Blob. So you can actually use HSM functionality to move data back and forth between the IaaS Lustre cluster and Blob storage for data that's less active and not necessarily needed at that particular time. We also here in the example have a few Azure NetApp Files volumes that are serving the low latency NAS functionality. And then if you see here, the on-prem users are actually connecting to a high memory GPU based cloud visualization workstation for any of those visualization requirements. The one thing that I'll note here is that you can see that at this point, the jobs are being submitted directly into the cloud for cloud compute resources. So there's no communication between the head node on premise and the head node in cloud. That's going to change in the next one, right? So now you'll see there's a couple of additional changes that we made here. So for this hybrid burst scenario, the changes are going to be where some customers will actually, they'll opt to leverage that schedule on premise or in parallel to the one in the cloud to burst that workload directly to the compute queues that are defined with cloud compute VMs. So now they can actually queue up jobs on premise, and then that job will spin up resources in the cloud directly from the head node that's on premise. Or you can also leverage in parallel a head node that's running in the cloud. The other component that we added here that we'll typically use when on-premise data needs to be available in Azure. So we'll leverage the HPC cache technology to maintain that active data cached in cloud, which eliminates any bandwidth or latency concerns when accessing that on-premise data. The other thing that I'll note here is that some customers may actually opt to skip this hybrid phase and move directly into the next phase, which is really the cloud, more the cloud optimize or entire in-cloud workflow. So when, as the customer may opt to minimize or eliminate that on-premise data center footprint. So for a lot of our customers, that's really their goals. They're trying to get out of the data center business. So the in-cloud workflow now has all the compute and storage assets running in Azure, where we can leverage really the optimal resources on a per job basis and streamline performance and the efficiency of those jobs. One of the main benefits here is that you can actually change the model of running your workload so that you're now specifically looking at which VM sizes and types are going to be optimal for specific jobs. And you can really tailor it to make the most efficient use of those resources. In this example, we also can add, if you need, if there's a requirement for more permanent or higher capacity throughput requirements, we can also leverage a fully managed bare metal cluster store offering, which is very high capacity throughput Lustre capabilities, and that gets wired directly into the customer virtual network for access. as I mentioned before, for many customers, this is going to be the end goal in terms of optimization workflow, where they really have no need or desire to change the application itself. But others will actually go to the next step to take advantage of even deeper integrations into the Azure ecosystem. So now looking at what a fully cloud native workflow would look like, this is an example of a 3D reverse time migration workflow that leverages actually machine learning in Azure for pre-processing and pre-run optimizations. And then Azure Batch for cloud native scheduling. So here we're not using any third-party schedulers. This is the fully native Azure Batch written directly from application into the Batch API. And then we're also leveraging Azure functions and storage queues to interleave data results that then get natively stored in the direct access object blob storage. So for applications where you can modify, you have the code, it's your own application, and you can refactor or rewrite those to really take advantage of batch and storage APIs. These types of workflows can really provide some of the most efficient high performance computing available today. So this would be sort of the end of the line in terms of native workflow as well. So, hopefully that information has been useful and really worthwhile. The one thing that I'll leave you guys with is, with the phase approach we've developed, working with lots of customers to date, that movement of HPC workloads into Azure produces not only, from what we've seen, fast, efficient, and really cost-effective results, but also allows us to leverage all the benefits that the cloud has to offer in terms of things like scale, flexibility, value add as you grow and transform those workloads to meet the business objectives, right? So that's really the key for us is we want to help customers not only become more efficient, but also cost effective with higher performance to boot. Right? So that's what I've got for everyone. In terms of questions, if you have anything for me, you can go ahead and send it directly to my email or contact Ron. So Ron, again, appreciate the opportunity to present today.